especially his family. And he's going to be speaking on a new algorithm for maximum flow distribution networks called the modified push algorithm.
All right, good afternoon. This is research I've been working with Dr. Karloff for the past year now. Today what I want to talk about is, first off, what is a maximum flow network and how do you solve it? Also, what is a maximum flow distribution network and how do you solve it? And then finally getting into what our algorithm is, the modified push algorithm, and then future research. So modified maximum flow network is a graph G that's made up of a set of nodes and arcs. The nodes are source nodes denoted by S, and you can have multiple source nodes for the network. And with your source nodes, you have one arc entering and multiple arcs leaving. You also will have a set of ordinary nodes, also denoted by O. And these represent companies that will just transfer the source straight through them. And with this ordinary nodes, you have multiple arcs entering, multiple arcs leaving. Another type of node is termination nodes, also called sink nodes. These represent where the final destination of where the material is going. And with your termination nodes, you can have multiple termination nodes. And with the termination node, it has multiple arcs entering, one arc leaving. Then the last type of node is pseudo-nodes. And these are just artificial nodes that enter our source node and leave our termination node. And we use these to determine how much flow is entering and leaving our network. Our set of arcs is what connects all of our nodes. And on each arc, you're going to be able to know what the capacity of that arc is, the lower bound or the demand for that arc, and then the current flow for that arc. One thing we've also assumed is all of our nodes are going to follow conservation of flow, which means what flow enters the node must equal what leaves the node. All right. Now, how do we solve a maximum flow network? Well, one way is by using the linear programming problem, or LP. And what we're trying to do is we're trying to maximize the flow leaving our termination nodes, subject to all the conservation of flow for each of the arcs. So the total flow into an O node must equal the total flow out. And then the same thing for our source node. The flow into a source must equal its total flow out. And then for a termination node, the flow leaving termination must equal the total flow leaving. Then the other restraints are the flow at any time on any of the arcs has to be between 0 and the capacity. Also for termination nodes, for the arc leaving, they must be greater than the lower bound, because we're assuming here that all of our termination nodes have a lower bound, a minimum demand. Then the last one is the flow leaving or entering our source node must be less than or equal to its capacity.
Can I interrupt you just a second? Because I want to, because there was a lot to read.
Okay.
So the ordinary nodes are always going to have a lower bound of 0?
Correct.
Okay.
We're assuming all of our O nodes will not have a demand, so whatever comes in will leave it. The only nodes that have a minimum demand are going to be our termination nodes, because those represent final stores where they're going to sell.
Excellent. Got it. Thanks.
No worries. All right, so now, how else can we solve our maximum flow network? Well, we can solve them algorithmically, and there's two different ideas to solve it algorithmically. The first way is by finding and creating augmenting paths, which means you're going to start at your source node and add in arcs such that they're not at their capacity. You're going to keep adding in these arcs one by one until you can get down to a termination node. Then you'll calculate the increment of flow for that path, add that flow on, reset the flows, and then keep creating these augmenting paths until you can no longer create an augmenting path, and therefore you will have the maximum flow for that network. The other type of algorithm is going to be what's created by Goldberg and Tarjan. It's similar, but what they do is they're going to start at the source node, push all the flow they can through the source node, so all the nodes leaving now will have excess flow. And then they're going to push that excess flow node by node until it reaches a termination node, because we push that excess through our termination node. And one restriction that they use, other than arcs that are not at capacity, is they calculate a distance a node is from the termination node. And they're going to keep pushing the excess flow forward until it either goes through the termination node or they must backtrack it through a source node. So they're trying to get rid of the excess flow on the network. So once the network does not have any excess flow, we therefore have the maximum flow for that network. Now, what is a maximum flow distribution network? It's the exact same as a max flow network, but with the addition of one other type of node called distribution nodes, or D nodes. And they're going to be similar to a source node where they have one arc entering and multiple arcs leaving, but what makes them different is the arcs leaving the D node are going to be proportionate to the incoming arc. And the way we denote that proportion is by KDJ. And this proportion just tells us how much of the flow is going to go along the arc. So for example, here on D1 to O2, 80% of what enters D1 is going to go here. Now, how do we solve this with an LP? Well, we're going to have that same problem that we did for the max flow, but with two added restrictions. The first restriction is to keep the conservation of flow. So the flow entering our D node, or no, leaving our D node must equal the proportion for that arc times the entering flow. And that's going to be true for all of the arcs leaving our D node. The other restriction is our proportions have to be greater than 0. We've also taken this restriction and made it even further. Each of our D nodes will have all their proportions add to 1. So looking back here, we want all of our proportions to add to 1. With other research, you can have it add to greater than or even less than 1. Okay. Now, how do we solve this algorithmically? Well, we will not be able to try to create an augmenting, we won't be able to create an augmenting path, but what we're going to be able to create is unsaturated subgraphs, which mean about the same thing for augmenting path. All the arcs in our network will not be at capacity. And we're going to start at a source node and add in our arcs one by one that are not at capacity until we reach a termination node. Then we'll calculate the increment of flow for that subgraph, add that increment back on, and then keep creating unsaturated subgraphs. And when we can no longer create an unsaturated subgraph, we therefore have the maximum flow for our network. Okay. So now that leads us into our algorithm, the modified push algorithm. This algorithm is a combination and modification of 3 different algorithms. Wang and Lin's compact algorithm, Goldberg and Tarzan's generic max flow algorithm, and Schuting and Wang's D algorithm. And the components for our algorithm is going to be to reset the capacities, then push our flow forwards, push flow backwards, then determine if we have an initial feasible flow, and then determine if we have a max flow. All right. So this is the network we created, and we just created it in a way such that it was very complicated so that we can try to cover everything that we need to in our algorithm. And as you see right now, it has a total entry capacity of 2,000. So that's going to change once we reset our capacities. So why do we reset our capacities? We're going to reset them so that we don't push too much excess flow through a node, because we want to keep our conservation of flow. So we don't want to push 500 to any node that can only take 300. And we're going to reset these capacities on arcs adjacent to D nodes, O nodes with an in degree of 1, O nodes with an out degree of 1, and then source nodes. Okay. So now for D nodes, if you just have a single D node, so it's not adjacent to any other D node, so if you just got this D node and it's connected to an O and a T node, what we're going to do is we're going to take, and also the entry, is we're going to choose some variable which is going to represent the reset capacity, and we're going to set it less than or equal to the entry capacity into the D node. And then for each of the arcs leaving our D node, we're going to take the proportion on that arc times our variable less than or equal to the capacity for each of the arcs. And then we're going to take the minimum of that. We're going to solve for x and take the minimum, because that's going to tell us the maximum capacity we can push through that D node. Now, what happens if we have D groups, which means you have multiple D nodes adjacent to each other? Well, you're going to use the first 2 restrictions, but then add on the last restriction of multiplying the proportions through the D node. So for example, if you've got this D node that has, say, 0.5, and here you've got 0.6 and 0.4, we're going to just multiply 0.5 times 0.6, and then times our variable less than or equal to the capacity, 0.5 times 0.4 less than or equal to the capacity. And we're going to do the same thing, take the minimum, because that tells us now the maximum capacity we can push through this D group. So an example of this, we're going to set x less than or equal to 500, then 0.5x less than or equal to 200, 0.5x less than or equal to 249, 0.3x less than or equal to 126, and et cetera, et cetera. So we're going to create this system of inequalities. We solve for x.